Alright, so in this video we're looking at electrostatics. So problem 2160 from University Physics, Young and Friedman. We've got two charges placed on the x-axis, one of 2.5 microcoulombs at the origin and the other is going to be minus 3.5 microcoulombs at x equals 0.6 meters. So find the position on the x-axis where the net force on a small charge, so a test charge plus q, would be equal to 0. So, okay, let me just draw what we've got here. So we've got our x-axis, we've got our x-axis, no we don't. Now we've got our x-axis. We've got one charge at this point here, and then we've got another charge at this point here. And let me just remember which was which. So we've got plus 2.5 microcoulombs at the what we're calling the origin. So plus 2.5 microcoulombs, and then the blue one is going to be minus 3.5 microcoulombs. So we're now going to put a test charge of plus q, anywhere on that line, and what we're interested in is where on that line is the net force, the net Coulomb force between our test charge plus q and our plus 2.5 and minus 3.5 microcoulombs. Where is that force going to be equal to 0? So the idea here is that the positive force from the 2.5 microcoulomb charge is going to repel our positive test charge, everywhere along the x-axis, and our minus 3.5 microcoulomb charge is going to attract it everywhere along the x-axis. So if we look at the three possible places it can be, so it can be here, here, or here, 1, 2, or 3 in regions of space. So if we take region 3 first of all, what we find is if we place our test charge anywhere on region 3, we've got a plus 0.35 we've got a minus 0.35 microcoulomb force attracting it at all times, and we've got a plus 2.5 microcoulomb charge. The force from that is going to be repelling it at all times. So in this region of space, in region 3 here, the attractive force is always going to be greater than the repelling force because of this larger force that we've got here. So what that tells us is that the force cannot be equal to 0 anywhere in this region here. Similarly, if we look at region 2, what we find is that we've got the attractive force that's pulling the charge. So let's say we put our plus q at this point here. We've got the attractive force which is pulling it towards the 3.5 microcoulombs, and the plus 2.5 microcoulombs is repelling it. So both of those forces are propelling our test charge in this direction. They're both acting together. So what that tells us about this region of space is that the net force on our charge is not going to be equal to 0 at any point either. So the last region we want to look at is the region that I've labeled 1 there. Now in region 1, the minus 3.5 microcoulomb force is pulling it towards us, and the plus is pushing it away from us. And the idea is, if you think about that, the way that's set up, there's going to be some point in space here where we're close enough to, let's put this guy in black here, we're close enough, get the right pencil, we're close enough to the plus 2.5 microcoulomb force that it's pushing us away, and we're nice and close to it, so it's feeling a strong force from that push. And the 3.5 microcoulomb force over the other side is pulling it towards us. Now it's got a bigger force, but it's much further away. And the idea is that there's going to be a balance point somewhere where our plus q feels no net force. So the force between the attraction to the positive charge and the repulsion from the negative charge is equal. Right, so the next thing we're going to do, now let me just remove some of this stuff here. The next thing we're going to do is try and make an equation. So we know that the forces are balanced wherever the net force on q is equal to 0. So let's call this guy, let's call this guy q1, let's call this guy q2, and let's talk about the forces between them. So we know that the force between q1 and our positive test charge and q2 and our positive test charge are going to be balanced at the point where q1 doesn't feel any net force. So what we're going to do is we're going to apply the fact that from Coulomb's law, F is equal to the magnitude of Q1 times Q divided by R squared, where R is the distance between them. So we're going to apply this to both Q1 and Q2 and take account of the fact that they're equal. So F F1 is equal to F2, where the net force is 0, and they're balanced. So that allows us then to write K times, so K is the constant, times Q1 times Q, which is our test charge, over, and we'll call it D squared here, so we're interested. So this is going to be the origin, so this is our 0 point here, and D is in this direction here. So how far do we have to go out along the x-axis to get to it? So this is the force, related to Q1, and that's going to be equal to the force related to Q2. So let's write down the force related to Q2 now. So we get K times the magnitude of force Q2 times our positive test charge Q divided by. Now, how far is our test charge going to be from Q2 at this point? It's going to be a distance D plus 0.6 meters, because the question told us that the distance between here and here was 0.6 meters. So when our test charge is a distance D from Q1, it's going to be a distance D plus 0.6 meters from Q2. So that, now we have our equation set up, and that should be squared. So sorry, I forgot my squared here when I was too busy talking. So now there are lots of things that we can cancel out here. So let's put it in red. We can get rid of K here because that's common to both sides. We can get rid of Q because that's common to both sides. And we can now simplify this equation. And the equation comes out to be, after we simplify it, D is equal to, because we were working with magnitudes, we get plus or minus the square root of the magnitude of Q1 over the magnitude of Q2. And that then is going to be multiplied by our D plus 0.6 meters from above. So now we can solve that for D. And remember, D, the positive direction for D is in this direction here. So this is positive for D. So D is, we're looking out along the negative x-axis and seeing how far we have to go so our forces will be balanced. So when we solve for D, we get D equals 0.8452 times 0.6 meters over 1 minus 0.8452. So this is just when we simplify our equation above and solve for D, we get 3.27 meters. So, D is positive, so we'll write that down here. D is positive, and it's 3.27 meters. So from charge Q1, looking out the negative x-axis, we see that D is at a distance of 3.27 meters. If you want to put it in terms of the x-axis, we can say x equals minus 3.27 meters. That's the point where we're going to find our charge, such that the forces on it from Q1 and Q2 are balanced. So Q1 is going to be exerting a repulsive force on it, pushing it sort of further out the negative x-axis, if you like, and Q2 is going to be applying a attractive force to it and pulling it towards the positive x-axis. And the point where those two forces balance each other is at the position x equals minus 3.27 meters.